Hi everyone, we're NeurotechSC, the UC Santa Cruz chapter of NeurotechX, and our project this year deals with phoneme recognition using FEMGs, which are just facial EMGs that go along the jawline. And my name is Nivriti Bopparaju, and I'm the president.
I'm Mathew Sarti. I'm one of the administrators.
I'm Chris Bjordahl. I'm one of the hardware team co-leads.
I'm Dennis Koshta, the data and machine learning team lead.
I'm Rico Rodriguez, and I am also an administrator and also the software team lead.
So why phoneme recognition? So first, just introducing what phoneme recognition is. It recognizes the small units of sound that are present in the alphabet. So one of the major goals that comes from this is word recognition from facial EMG signals. And then this would allow for subvocal speech transcription for communication. And then a couple applications of this are for people with disabilities, since not all people are capable of producing vocalized speech. And then another application would be human-computer interfaces, which would allow for technological progress and exploration.
Regarding the neuroethics of our project, data ownership is only given by consent of the user. Data acquisition and bias, we try to unbias the data by diversifying where we collect the facial EMGs from. But for our final model, the data was recorded using Chris's face, so that might be difficult to generalize. Technological use and ethical considerations, it's open source, so it's able to be replicated and verified from whoever has access. For the overview, we will start with the face. There we will collect EMG signals through the OpenBCI open source Cyton board, the picture there. There we also see Chris with the dry electrodes on his face. The data will then be passed over to ML. Here we see a picture. This will then be sent to the software team where they will predict the phoneme in a nice graphic user interface.
Okay, so first we're going to go over hardware. So for our job as a hardware team, we recorded data for the machine learning and data team to implement into a model. The procedure for recording was intricate and precise to utilize the muscle groups we used to the best of our abilities. And the muscle groups we used were the four shown in the picture on the right. These muscle groups gave off the best activation using the BCI board, especially for phoneme recognition. For the actual procedure, we had the board set up with a button and a microcontroller in between them. The breadboarded button was used to mark recordings. The microcontroller was used to connect the breadboard to the OpenBCI board so that it was all in one place and it was streamlined. The board itself, we had 4 channels set up, each having a dipole so that we could have 2 electrodes per muscle group, and a 5th channel as set as the bias so that there would be noise cancellation and more conciseness, especially for 250 hertz, which is what most areas and technologies use. For the mask, due to time constraints, we weren't able to implement the mask, but it would have been useful to have, especially for more accurate and efficient recordings, and especially so for more diverse groups, because the mask would have been set up as variable sizes, as you can see in the top picture. Variable sizes for variable faces, variable sized muscle groups, etc.
And so moving on to the data and machine learning aspect of things, after the hardware team collected various data sets, we would get a CSV file with it. And it basically went first, we got like the first 5, then we chose 22, and eventually we got to all 44 phonemes. As well as with the final recordings with the 4 muscle groups, we basically used, we recorded the phonemes as well as some words, sentences, phrases, and a paragraph of text. A brief overview of the pipeline would be that we first filter the columns to get the necessary ones that we use. We remove the outliers and then use min-max normalization, which you can see the effects of on the right side of your screen, showing the 4 muscle channels and then the 5th button channel that we use to actually mark the segments, which we identify 10 segments per phoneme, 44 phonemes, so 440 segments total, as you can see at the bottom of the screen, with some other statistics about those segments. Then we use a sliding window technique to generate equal-sized training examples from those segments. And we experimented with different window sizes like 5, 10, and 30 values. And using those as training examples, we made an X train and Y train with the data and then labels into a NumPy format that we could then pass off to our machine learning models. And within machine learning, we took that data. We first considered the use of a TMC VIT architecture, which used transformers and convolutions and temporal multi-channel features, but it ended up being a bit too complex and overkill for a problem like this. So we switched to an LSTM RNN type architecture, which was more simple and surprisingly effective for this problem. So we decided to stick with that. As we got those data sets from first hardware, then we would process it, and then to machine learning, we kept basically the same network hyperparameters in our architecture, and would just experiment with different small changes to see their effects. We did a standard 80-20 split. We used a sequential model with the convolution layers, LSTM layers, and fully connected layers. We experimented with a variety of model sizes ranging from hundreds of thousands to millions of parameters. And we eventually achieved 98.1% accuracy on test data with only about 200,000 parameters, which was very impressive and efficient. And as you can see, there's the loss and accuracy graphs where loss should be trending down, accuracy should be going up. So that looks good. We use various techniques such as dropout to prevent overfitting. And there are some data concerns whether training on data that is singular phoneme pronunciation will actually transfer over to predicting phonemes within continuous speech. But that is something we have addressed. And in order to actually evaluate our model, we use something called the confusion matrix, which basically shows the rows are the actual phonemes, and then the columns are which phoneme is predicted. So along the diagonal, those are true positive predictions, which is good. Outside of it is bad. As you can see circled there, 6 of the silence phonemes were actually predicted as EHs, so that can give some insight on where the model or the data might be lacking.
Now moving on to the software aspect of this project. As for our software team, our responsibility was to connect the machine learning model to a user interface and to record data. We weren't able to fully realize our initial plans for implementing a user interface due to limitations with how the model was trained and how it behaved. For our proposed architecture, the plan was to have an OpenBCI EMG data stream to the machine learning model, which had 2 threads, one for listening to that data stream and one for classifying phonemes and sending them to the user interface. We were going to have the classification model and the user interface in a Docker container to streamline deployment and development. As for our proposed user interface, which again was not realized, the plan was to show a live transcription over 10-second intervals to the user. The user would then be able to classify whether the prediction was correct or incorrect, and the result would be recorded into a database with the prediction and the user classification. For the future, if this was realized, the plan was to pass this prediction to another machine learning model to then predict text and display that to the user as well. As for what we tried for our user interface, our first attempt, we attempted to make a web app using Flask and Python with our machine learning model and GUI in separate processes. The cause of this was that we would need a WebSocket to pass data back and forth. Not everybody was familiar with creating an API, and it a bit overkill and unnecessary for our use case. And we would use MongoDB to store the data. For our second attempt, we used Python with tkinter and our machine learning model and user interface in the same process. Now, this came with benefits such as tkinter comes with the standard library for Python. There's a lot less overhead with having a web service up. We would have shared variables instead of having to send messages through a WebSocket. It's simpler and easier to learn, but the cons of this was that we weren't able to containerize this due to limitations with tkinter. And likewise with the first attempt, we would also be using MongoDB to store our data. And so now moving on to our demo.
Here we have a few pictures of the data collection setup where the electrodes are placed and the various hardware. And we have a video of one of our recording sessions where we record 5 phonemes, a word pronunciation, and then a test sentence that contains lots of variable phonemes. As you can see, the recording starts and the OpenBCI interface shows the signals. as the subject, Chris, pronounces those phonemes with his finger on the hardware button, pressing it down during the moment of pronunciation in order to mark it within the actual data.
The quick brown fox jumps over the lazy dog.
Some limitations regarding our project is background noise and spiking caused from electrode placement error led to wrong or just incorrect data. To correct this, we would require new hardware for more accurate and efficient data collection, such as replacing our dry electrode method with wet electrodes, the not actualized 3D printed mask, or FPGA board. More data collection would lead to better model performance, and ideally a streamlined recording protocol would allow for more effective and accurate recordings. Once this is all complete, we would finish by integrating the model and data processing into the live transcription app. Thank you guys for listening.